Our next speaker is Ju Soon from Computer Science and Engineering Department, and I'll ask Su Yang to prepare for the next talk.
All right, good afternoon. Disclaimer, I'm an AI researcher, but I'm going to tell you a material science story, so mind the human hallucination, okay? So when people try to do AI-driven material discoveries, two of the most important steps, one is that you need to come up with some material candidates, that's the generation step, and the other one is that you want to predict the properties. So when people want to predict the properties, there are two competing approaches nowadays. One of the approach is computational simulation. People familiar with material science probably know DFT well, so which is a very, very basic computation in material science, which is not discrete Fourier transform, it's the density function theory, right? Okay. Which can take this to actually, try to characterize the property of a given material. Now, people are thinking about trying to shift more and more to machine learning models, which after training, you probably can do the prediction by one pass, which is probably just several seconds, if not less. By the way, so this whole project is funded by ACID, which I heard is largely inspired the second iteration of KGML workshops, right? I learned from Vipin. So we are very grateful to this, but unfortunately, this program was actually recently canceled by NSF. We get the money to do the research, but unfortunately, there's no future iteration of this. So material scientists, nowadays have collect large-scale training sets. They have up to like 1 million training data points in their public data set. But something they didn't do up to this point is this. Okay, so one of the most important properties they want to predict is something called thermal stability, which basically means if you come out with this material, whether the material can quickly become other material, which basically means the material is not stable and that's useless, right? So they know a lot about what kind of materials can be stable and what kind of material cannot be stable. For example, for the same chemical composition, you can have different topology of that, what they call a polymorph, which basically means different critical structures of the same composition. They can have different energy level. The one with the lowest energy level would be the stable one. And there's something even more complicated that I'm not going to explain here. That's called a phase separation. From high level, that just means whether a material can quickly become other materials. So up to this point, as I said, when people are training their property prediction models, they are not taking this into account at all. So what we found is that there are quite a number of these physical laws that can be mathematically formulated rigorously, and after that, you can put these kind of constraints into the training process. And from there, you can benefit quite a bit after training. So what we show quickly here is that, after we incorporate this basic level physical laws, we can boost their F1 score, which is kind of accuracy, but also capture how sharp their prediction is by 5%. But this is just a basic one. We can do much more than this. And several seconds left. So talking about enforcing constraints, and I think this workshop is also about enforcing constraints. I want to make a point that a lot of people are talking about constraints, but we often put a constraint as regularization in training, right? Our reasoning is always that, okay, we don't have to respect all constraints, which I agree, but some of the constraints we have to respect, I think. And also, even the constraints you don't have to strictly enforce, you probably still want to have some control. That means it's much better actually, when you come to mathematical formulation, you say, okay, the violation can be more than certain quantity, certain amount, rather than leave that regularization. So anyway, so if you have these kind of hard constraints, so my group is actually developing some deep learning framework that can handle these hard physical constraints. We are working with operational expert to develop these kind of computational tools and also modeling language. So if you are interested, you are welcome to chat with me afterwards. Thank you very much.